Good afternoon, friends, and welcome to another physics topic. Today, we will be doing another topic of physics, class 12. So, as you can see, today's topic will be dual nature of light, that is, matter. Here, we will be dealing with matter, and which will be about light. So, we will be studying the dual nature of light, how the light will be dealt. We know generally light is of wave nature. We have studied light about its wave nature, and now today we will also be studying about the particle nature of light, that is the wave nature, about the wave nature and about the particle nature of the light. So that is the dual nature of the light that we will be studying today. So this is, as you can see, this is my personal guidance number. You can contact me over this. You're watching Parijat sir classes. Please like, share and subscribe my channel so that I can be motivated to make more and more videos for you. Okay. So without wasting any time, let's move ahead to the topic of dual nature of light. Okay. So see, as you can see from here, the phenomena of interference, diffraction, polarization. These are the three phenomena: interference, diffraction and the polarization of light. Establish that light is of wave nature. Please understand this thing, that these are the three phenomena: interference, diffraction and the polarization. What did it establish? That light is of wave nature. Okay, these three phenomena establish that light is of wave nature. Next, J.J. Thomson predicted that cathode rays are nothing but stream of fast moving electrons. Cathode rays are nothing but stream of fast moving electrons. It was discovered that cathode ray particles were universally alike. Later on, scientists discovered that electrons are fundamental particles. So what was cathode rays? Cathode rays was generally constituting of particles. Okay, cathode rays was generally made up of particles. Now, these particles were later found that these are actually electrons. These particles were later found that they are electrons and are universal constituent of matter. Millikan, another scientist, Millikan experimentally measured the charge on droplets and predicted that charge on a droplet is integral multiple of electron. That means Millikan also showed that any oil drop was actually having charge which was an integral multiple. It was having charge which was integral multiple of the charge of an electron. That means if you are having this as 1, 2, 3 like this, that means this Q is an integer. Q is an integer, and that means this is a particle. This is a particle. Okay, this behaves as a particle. This oil drop behaves as a particle. So he also proved that the charge on the droplets are integral multiples of the electron's value. This shows that charge on a body is quantized. That means you cannot have fractional values. Quantized. Okay. Next is the photoelectric effect and the Compton effect. These are the two important effects, the photoelectric effect and the Compton effect, explained the quantum theory of physics. Quantum theory, that means these three established the wave theory of light, and these two established the particle nature or the quantum theory of light. These two established the quantum theory of light. According to this, light consists of packets of energy which travel in straight line. He told that light is actually, if light is traveling like this, that means it is having some packets of energy. It is having some particles of energy which is traveling with the light. Particles of energy. Okay, the quantum theory says that. According to this, light consists of packets of energy which travel in straight lines with the speed of light. Each packet is called photons. So these are the photons. These are the photons. Okay, they are packets of energy which travel in the direction of the light. And what is that energy? H nu. That energy is actually H nu, which is hc by lambda. H is the Planck's constant. Nu is the frequency of light. C is the speed of light, and lambda is the wavelength of the light. Thus, particle nature of light was established. That means these two theories actually predicted the particle nature of light, right? So what is happening here? So what we are seeing? We are seeing that some phenomena of light were explained by the wave theory, like these, and some by the particle nature, that is the Compton effect and the photoelectric effect. Hence, it was concluded that light is of dual nature. It was concluded that light is actually of a dual nature. So this is the main thing what we are going to study, that light is actually having a dual nature. That means sometimes particle nature, sometimes it is having a wave nature. Next, we will be studying work function. We will be studying the work function. So what is work function? What is work function? Work function of a metal is the minimum energy required by an electron to just escape from the metal surface so as to overcome the restraining forces of the surface. For example, this is a metal, okay? So these are many electrons on the metal. These are the many electrons on the metal surface. Let us take about metal surface. When light is falling on this surface, having some energy, when light is falling on this surface, having some energy. Now, suppose these electrons are bounded with an energy this much. Now, when light is falling with an energy which is greater than this energy, then only the electrons will be liberated. Then only electrons will be liberated, otherwise not. Okay, so when light energy which is incidented is greater than the energy of the electrons on the surface, then only the electrons will be liberated. So this is the minimum energy required for the electrons to escape from the surface. Clear? Next is photoelectric effect. Photoelectric effect. So what is that photoelectric effect? It is the phenomena of emission of electrons. So these electrons which are coming out, that is the phenomena of emission of electrons from the surface of metals when radiations of suitable frequency fall on them. So see, the radiations, this is the radiation which is falling. This is the radiation which is falling on the metal surface. Okay, 1 minute. Let me make this little bit easy to you. Okay, so suppose this is the surface. This is the surface, and here are some bound electrons on the surface. Here are some bound electrons on the surface whose minimum energy is phi. Now when electrons of energy, suppose this is the energy which is striking on the surface, h c by lambda, okay, which is greater than the work function. So then what happens? electrons will be emitted from the surface. These electrons will come out. These electrons will come out. Okay. So when energy greater than the work function is emitted, so electrons will come out, and that is called photoelectric effect. This is called photoelectric effect. Next we will study the threshold frequency. Threshold frequency, what is it? What is the threshold frequency? If the frequency of the incident light, so this is the incident light, this is the incident light, if its frequency is smaller than a certain minimum value called threshold value frequency, there was no emission of electron from the surface. So the light which is incidented on it, if the incident frequency is less than the threshold frequency, that means minimum frequency required to liberate the electrons, then we will see no emission of electrons are taking place. No emission of electrons are basically taking place. Okay, so you have to give a frequency. The incident frequency should be greater than the threshold frequency, then only photoelectric effect can take place. Next, please watch here. This is the emitter C. As you can watch here, this is the emitter. Okay, A is the anode. A is the anode at the positive terminal, and C is the negative terminal. So A is also called the collector. A is also called the collector, and C is called the emitter. Now watch here, the plate A is connected to the positive terminal, plate A is connected to the positive terminal, and plate C is connected to the negative terminal, and here is a voltmeter. So you can measure what is the voltage of the plate A. Here is a microammeter which can show you the reading of the current. Now what happened? This is the incident, and you can watch here, an incident light is falling on the metal surface C, that is the emitter. This is the incident light falling on the metal surface C. Okay, so after this we can see the electrons are coming out, and these electrons having a energy. What is the energy? Energy of each electron is h nu, because they are treated as packets of photons. Okay, so they are attracted towards the positive plate of the battery. So more is the emission, more is the electrons getting collected on the plate A, so more is the reading of the microammeter. Clear? So what we can see, that effect of intensity of the incident radiation. So this is the radiation which is incidented. What is the effect of intensity of the incident radiation? Keeping the potential difference across A and C constant, if we vary the incident intensity of the radiations. So watch here, what is happening? Photoelectric current varies linearly with the intensity of the incident radiation. So please watch here. As the intensity increases, the photoelectric current also increases. So it is a linear graph. As the intensity of the incident radiation increases, the photoelectric current also increases. Okay. Next we'll be studying, first let us, so this is the effect of the intensity of the incident radiation. That means more the intensity, more is the photoelectric current. The photoelectric current varies directly with the intensity of the incident radiation. So this is the graph. Next we want to study what is the effect of potential of plate A with respect to plate C. Okay, so let's see this. Plate A, keeping the frequency. So first we will keep the frequency and intensity of the incident radiation constant. First, intensity and frequency of the radiation will be kept constant. Now what we will do? We will slowly increase the positive potential of the plate A. and so we will find that the photoelectric current also increases gradually. So when we increase the potential of the plate A, the photoelectric current also increases. So at one stage, what will happen? The photoelectric current becomes maximum and does not increase on increasing the potentially. So watch here, till here, as the potential increases, please watch here, as the potential of the plate A increases, the current also increases. You see, current also increases. This is for if I keep the intensity constant. Okay, as the potential increases, the current also increases. Now, till it becomes saturated. So from here, watch, it has become saturated. So if I take a higher intensity, so same thing will happen. As the potential increases, current increases till it becomes saturated. As the potential increases, the photoelectric current increases till it becomes saturated. Now that saturated, that is called the saturation current. That is called the saturation current. Now what we will do, apply a negative potential on plate A. We will apply a negative potential on plate A. So see, the potential of the plate A is gradually decrease. Okay, the photoelectric current, as you can also see, the photoelectric current now goes on decreasing. If I keep decreasing the negative potential on A, so see the photoelectric current, they also goes on decreasing. They also go on decreasing. If I decrease the photoelectric current, if I decrease the potential of the plate A now, okay, the photoelectric current also goes on decreasing till at a particular negative potential of the plate A, the photoelectric current becomes 0. Okay, so now if I keep on increasing the negative potential at a certain negative potential, this is minus V0. So what we will see that the photoelectrons stop reaching A and the photoelectric current becomes 0. That means at this negative potential, so as you can watch here, at this negative potential, the photoelectric on A, the photoelectric current becomes 0. The photoelectric current becomes 0. Okay, so now what will happen is, this is called the stopping potential or the cutoff potential. This is called the stopping potential or the cutoff potential. So what is stopping potential or cutoff potential? It is the negative potential at plate A where the photoelectric current becomes 0. Okay, so it is the minimum negative potential given to plate A with respect to C, as which the photoelectric current becomes 0. Now if m is the mass of the electron and V max is the maximum velocity of electrons emitting out, then what happens? See, this is the energy which is falling on the plate C, and then the electrons are coming out towards the plate A, which is positive plate. Okay, so that means if we apply a negative potential on plate A, we can stop the emission of the electrons. We can stop the emission of the electron. That means if I provide this much of energy at plate A, that means the electrons which were coming out with this much energy could be stopped. Okay, as you can see here, if I increase the negative potential, the current stops. That means electrons are not emitted. That means if I can provide this much of energy, negative energy on plate A, I can stop the maximum kinetic energy electrons from reaching the plate A. I can stop that. So the maximum kinetic energy of the electrons which can be emitted but not reaching the plate A is this, half m V max square equal to E V0. Next is, as the intensity of the radiation increases, the value of the saturation current increases. So as you can see, if I increase the intensity of the radiation, as you can see, if the intensity of the radiations are increased, see the saturation current also increases. The saturation currents, they also get increased. Okay. The stopping potential is independent of the intensity of the incident radiation. As you can see, all the stopping potential are concentrated at this. Whatever is the intensity, even if I increase the intensity, but see the stopping potential is fixed at minus V0. That means this is the ultimate stopping potential, minus V0. So we can tell that the stopping potential is independent of the intensity of the light. Okay, so let us first highlight it. The stopping potential is independent of the intensity of the incident radiation. Clear? Next, the maximum kinetic energy of photoelectrons depends on the radiation source and the nature of the plate, but is independent of the intensity of the radiation. So please watch here. The maximum kinetic energy of the photoelectrons is independent of the intensity of the incident radiation. Please remember this. If I increase the intensity of the incident radiation, the maximum kinetic energy will never be depending on that. Okay, please remember this, very very important thing. Next is effect of frequency of incident radiation. That means if I change the frequency of incident radiation, what can happen? So let's see. First of all, as you can see, we are taking different frequency of the incident radiation. The value of the stopping potential is different for radiation of different intensity. As you can see, this is the lowest frequency, the stopping potential is up to this much. Then this is the higher frequency, the stopping potential is up to this much. Then this is the highest frequency, the stopping potential is up to this much. So the stopping potential will be more if the frequency of the radiation is more. Next, the value of the stopping potential is more negative for radiation of higher incident. As you can see, higher the frequency, higher is the stopping potential. Higher is the stopping potential. The value of saturation current, this is the saturation current, depends on the intensity of the incident radiation, but is independent on the frequency of the incident radiation. Please note that. So saturation current is dependent only on the intensity of the radiation, but not on the frequency. For a given photosensitive material, the stopping potential varies linearly with the frequency of the incident. So watch here. If the frequency is increased, see the stopping potential also increases. This much is the stopping potential. And if this is the frequency, then this much is the stopping potential. So stopping potential will depend on the frequency of the incident radiation. There is a certain minimum cutoff frequency. As you can see, this is the cutoff frequency. This part is the cutoff frequency, okay, called the threshold frequency, for which the stopping potential is 0. Please watch here that if the light is incidented with a frequency which is less than the stopping potential, the threshold frequency, the electrons will not be emitted and you will not get any current. The higher the work function, the greater is the threshold frequency. If this is more, then this is also more. The intercept on the potential axis, as you can see, this is the intercept. This is the intercept, and another intercept is this is another intercept. This is the intercept for the frequency nu1, and for the frequency nu2, this is the intercept. This is the intercept. So we can tell that the intercept, which is this minus phi 0 by E, okay, so the intercept, which is this on the stopping potential axis, work function phi 0 is equal to E into intercept axis. That means this intercept, which is given as minus phi 0 by E, intercept is given as minus phi 0 by E. Next, if the incident radiation is of higher frequency than of the threshold frequency, the photoelectric emission starts instantaneously. That means if the incident frequency is, suppose this is greater than the threshold frequency, that means photoelectric emission will be starting instantaneously. Very fast it will start. Clear? Next, laws of photoelectric emission. Laws of photoelectric emission. So see, what are the laws of the photoelectric emission? Number 1, for a given metal and frequency of incident radiation, the number of photoelectrons ejected per second is directly proportional to the intensity of the incident. So number of photoelectrons will be directly proportional to the intensity of the incident radiation. First point. Point number 1. Point number 2 says, for a given metal, there exists a minimum frequency of radiation below which no photoelectrons can take place. This is called the threshold. That means your frequency has to be greater than the threshold frequency. Then only electrons will be emitted. Above the threshold frequency, the maximum kinetic energy of the emitted photoelectrons is independent of the intensity of the incident light but depends on the frequency or wavelength. That means if incident frequency is greater than the threshold frequency, so then what happens? Kinetic energy of this is independent of the intensity of the light. Okay, it is independent of the intensity of the light or wavelength. Okay, but it depends only on the frequency. The photoelectric emission is an instantaneous process. The time lag between incident radiation and emission of photoelectrons is only 10 to the power minus 9 seconds. That means instantly the photoelectrons will start to be emitted. Instantly the photoelectrons will start to get emitted from the surface. So these are the laws of the photoelectric emission, which you have to memorize it by heart. You need to know this equation very, very nicely. This all the 4 laws of emission, very important. Let's see the next thing, Einstein's photoelectric equation. Light radiations consist of packets called quanta. One quanta of light is a photon. So they are telling that the light which is emitted The light which will be emitted or incidented, these are actually in quantas. So this is the energy of each photon. Energy of each photon which is hitting the metal surface C. Now this energy of photoelectrons is first of all hitting the metal surface C. So this is A. So this is the incident radiation H nu. Now some energy is used to overcome the attraction of the electrons, suppose it is phi 0, and the rest will be ejected out as kinetic energy. So we can write that this is the equation of the kinetic energy of the electrons emitted. Out of the incident energy, some energy is wasted to overcome the attractive force of the electrons, which is called the work function. Then the remaining of it is the energy with which kinetic energy of the photoelectrons. So this is Einstein's photoelectric equation. This is the Einstein's photoelectric equation. Clear? Next, if the incident photon is of threshold, that means if this is only the incident frequency, then the incident photon, this is the energy incidented, is enough to eject electrons from the metal without imparting any kinetic energy. That means, as you can see, this is our relation. This is our relation basically. Now if the incident radiation is threshold frequency, so we can tell that the nu is equal to nu 0 and this will be 0. Okay, this will become 0. So kinetic energy will be not there. That means only the electrons will be ejected but no kinetic energy. No kinetic energy. Okay, without any kinetic energy. If nu is equal to nu 0, we know that Ke will be 0. That means the electrons will be emitted out without any kinetic energy. Clear? If the incident frequency is less than the threshold frequency, kinetic energy is negative, which is impossible. Hence, photoelectric emission does not take place with incident radiation below threshold. Please note that if your incident radiation frequency is less than the threshold frequency, electrons will not be ejected out. If incident frequency is more than the threshold frequency, the kinetic energy will become positive and it will depend upon the incident frequency of the light. Photoelectric emission is possible only if incident light is in the form of packets of energy more than the work function of the metal. Okay, light is not of wave nature but particle nature. So photoelectric emission is possible only when light's incident frequency is more than the threshold frequency, and then only the electrons will come out with some kinetic energy. And if they have kinetic energy, that means they have mass and they are some particles. That means the photoelectric emission proves it is not wave nature but it is a particle nature. It proves it is not of a wave nature but particle nature, because electrons are coming out with some kinetic energy. Clear? Next, relation between cutoff potential, frequency of the incident photon and threshold. So watch here. This is our relation. This is the energy with which the light is incidented. Out of that, some energy is spent in overcoming the electron's attractive force, that means work function. So with the remaining energy, it comes out as kinetic energy. So if V0 is the stopping potential, that means we can write this. So we are actually stopping the maximum energy electrons to reach plate A. So the kinetic energy of the electrons will be EV0. Nu0 is the threshold frequency. So we can write like this. So using all the formulas, we are now putting it and we are getting, this is our formula for the relation between the cutoff potential frequency. This is the cutoff potential, this is the cutoff potential, this is the incident frequency, this is the threshold frequency. Okay, and since frequency is equal to C by lambda, so we can put it like this, and this is our relation when the electrons are ejected. Okay, here lambda is the, this lambda is the incident light's wavelength, and this lambda 0 is the wavelength when of the minimum frequency which can be emitted. Minimum frequency which can be emitted. Next, let us see frequency, nu and stopping potential. So see, this is the stopping potential and this is the frequency. So this is the threshold frequency. Okay, and this much is the intercept on the stopping potential. So please watch here. This is the minimum frequency with which light should be incidented to eject electrons. So we can write like this. So stopping potential will be this. Now this is actually acting as this equation, y is equal to mx plus c. Okay, so x is the frequency on the x-axis, y is the stopping potential on the y-axis, and this is slope and this is the y-intercept. So slope is actually this. This is the slope and this is the y-intercept. This is the y-intercept. So we can see stopping potential is directly proportional to the frequency of the light emitted. Okay, so these are given here. So these are the y-intercept is this much, x-intercept is this much. Now we are plotting the frequency and the maximum kinetic energy. So please watch here. Once the electrons start ejected, the electrons will come out with some kinetic energy. So we can write K max equal to H nu. This is the incident energy of the light. This is the work function. Okay, the minimum amount of energy required to overcome the electrons' attractive force, that is work function. So how much energy is left? This much. So that is the energy with which electrons will come out, kinetic energy. So we can see that the kinetic energy is proportional to the frequency of the incident light. Okay, this is our slope. This is the x-intercept and this is the y-intercept. This is the y-intercept. This graph is about frequency and stopping potential. So as you see, the the frequency increases. As the frequency increases, we see that the stopping potential for different metals are plotted here. Stopping potential for different metals are plotted here. Next, frequency nu and photoelectric current. Frequency and photoelectric current, we will see how do they vary each other. So let's see. This is the frequency increasing and this is the current. We can see only after a threshold frequency the electrons will come out and they will produce a current, which is the saturation current. After some time, we will get a current. As the frequency increases, the photoelectrons coming out will be coming out with maximum energy, and then they will become constant. That means the current will become constant. So I is independent of the frequency of light till the intensity remains constant. Okay. Similarly, relation between intensity and stopping potential. Relation between intensity and stopping potential. So see, this is the intensity goes on increasing, and this is the stopping potential. So you will see that after a certain stopping potential, this much value, although intensity increases, stopping potential remains constant. Also, although the intensity increases, so intensity and stopping potential, V0 is independent of the intensity of the incident radiation, independent, till frequency remains constant. Please note this. Okay. So stopping potential is independent of the intensity of the incident radiation. Next, time and photoelectric current. Time and photoelectric current. Okay, so let's see what is time and photoelectric current. As you can see, after a time lag of 10 to the power minus 9 seconds, then only electrons are ejected and they become constant. So this is the electrons ejected after a time of 10 to the power minus 9 seconds. So then the current becomes constant. Okay, current becomes constant. Initially, after a time lag of 10 to the power minus 9 seconds, the electrons are getting ejected. They travel towards the positive plate A. So the current goes on increasing. Okay, but after 10 to the power minus 9 seconds, the electrons, all electrons are reaching the plate A. So current becomes constant. Failure of wave theory of light to explain photoelectric effect. Okay, so why with the help of the wave theory we cannot detect the photoelectric effect? Why? So that is the main question. Why with the help of the wave theory we cannot explain the photoelectric effect? So let's see. According to wave theory, the energy carried by beam of light is measured in terms of intensity. So wave theory says that you have to measure the light's energy in terms of the intensity. When a beam of light falls on a metal surface, the energy carried by the light is distributed uniformly over the entire surface. So when a beam of light is falling on the metallic surface, its energy is distributed uniformly over the entire surface of the metal. All the free electrons on the metal surface will receive the light energy and will be ejected out. When the waves of light of higher intensity falls on the metal surface, it will impart more energy to the electrons, definitely, due to which the electrons will come out with more kinetic energy. This is against the particle nature, which states that maximum kinetic energy of ejected electrons is independent of the intensity of the light. So this is why the wave theory fails. Okay, they are telling that if an incident light falls on the metal surface, the energy is distributed uniformly over the entire surface of the metal. All the electrons on the metal surface will receive the light of energy and will eject it out. They are telling all the electrons will be ejected out. But it is seen that when light higher intensity falls on a metal surface, it will impart more energy to the electrons, due to which the electrons will come out with more kinetic energy. This is the failure. That if a higher frequency is being, if the higher intensity is being used, if we use a high wave light, higher intensity falls on the metal surface, they are telling it will give more energy to the electrons, due to which the electrons will come out with more kinetic energy. This is not possible. You cannot increase the intensity and tell more and more kinetic energy electrons will come out. This is not being followed. That is why with the help of the wave theory we cannot tell that more the intensity of the incident light, more is the kinetic energy of the ejected electrons. Next, according to wave theory, the photoelectrons emission is possible from a metal surface by the wave of light of all frequencies. They are telling that if any frequency falls on the metallic surface, the photoelectric emission will start. Okay. Obviously, provided the intensity of light is sufficient to provide energy to the electrons, definitely. It means by increasing the intensity of light, the energy can be increased and photoelectric emission will take place even if the frequency of the incident light is less than the threshold frequency, which is not possible. So this is against the experimental fact that no photoelectric emission takes place from a metal surface, okay, which is below the work function of the metal. One minute. Okay. So next, let's see, friends, if the frequency of the incident light is less than the threshold frequency, no matter whatsoever may be the intensity, okay, that means if the light incidented is less than the threshold frequency, if the light incidented is, if this is less than this, so light will never be the photoelectrons will never be ejected. So when the wave of light falls on a metal surface, the photoelectrons ejected from the surface of the metal will take some time. Here they are telling the electrons will take some time before they are ejected out. But this is against, because it is telling it is taking only 10 to the power minus 9 seconds. So that means it is emitted out instantly, immediately. So this is again a failure of the wave theory failure. Okay. Next we are going to study the dual nature of radiation. The light's dual nature. We are going to study the light's dual nature. Okay. So let's see. The phenomena like interference, diffraction, polarization, etc. can be explained on the basis of wave nature, definitely. So these are the three things: 1, interference; 2, diffraction; 3, polarization. These can be expressed only with the wave theory. Second, the phenomena like photoelectric effect, 1, Compton effect, 2, can be explained only by quantum theory. Third, phenomena like rectilinear propagation, light, reflection, refraction, can be explained on the basis of wave nature. That means there are certain effects which can be shown with the help of the wave nature of light, and certain which can be shown with the help of the particle nature of light. And that is why we tell light is of dual nature. Next, we are going to study de-Broglie dualistic hypothesis. That means de-Broglie's wavelength. Okay, so let's watch here. According to de-Broglie, a moving particle sometimes acts as a wave and sometimes acts as a wave or sometimes acts as a particle associated with the moving material particle, which controls the particle in every respect. The wave associated with the moving particle is called matter waves or de-Broglie waves, whose wavelength can be found out like this. So lambda is equal to h by mv. Okay, this is how we can find out the wave length of the de-Broglie wave. H is the Planck's constant, mass of the electron, photon, and velocity of the photon or the particle. So this is the connectivity between the wavelength of the wave and the particle nature, and de-Broglie told using these formulas together we can find out the de-Broglie wavelength of the wave. Next, derivation of the de-Broglie wavelength. How to find the de-Broglie wavelength? So let's see. According to Planck's quantum theory, the energy of the photon is given by this. Again, Einstein theory says that the energy of a photon can be given by this. So equating them, we can get the mass of the photon. We can get the mass of the photon. Okay. So what is the momentum? Momentum is mass into velocity. So this is the mass into the velocity, which is coming out by this. And nu by lambda, nu by c equal to 1 by lambda. So the formula comes out to be this. So please remember, lambda is equal to h by mv, and p is equal to h by lambda is again an important formula. P is equal to h by lambda is an important formula for our numericals. Okay. So from here we can see that if the velocity of the wave is 0 or of the particle is 0, the wavelength is coming infinite according to this formula. According to this formula, if v equal to 0, lambda equal to infinite. Similarly, if v is infinite, wavelength is coming 0. That is, waves are associated with particles. So when the wave is, watch here, when the wavelength cannot be infinity, so when the wave particle is moving, okay, which are in motion only, then only you can find the de-Broglie waves, which are cannot be, okay. So now we know electromagnetic waves are produced by motion of charged particles. We know electromagnetic waves are produced by motion of charged particles. That means when there is a motion, of the particle, then only we are getting the wavelength. Okay. So they are telling that de-Broglie waves cannot be electromagnetic waves in nature, as electromagnetic waves are always produced by motion of charged particles. Always produced by motion of the charged particles. When there is a motion, so when there is a motion, then only you get the waves, that is electromagnetic waves. So de-Broglie told that if you move a particle, then only you will get a wave. So it is not actually electromagnetic wave. It is not actually electromagnetic wave. That means if a particle is moving, you get a wave whose wavelength can be found using this formula. Another one, relation of De-Broglie wavelength and temperature. How will the temperature and the wavelength get interlinked? So let's see. This is the formula of temperature with the wavelength. This is Planck's constant, this is mass of the particle, Boltzmann's constant, and this is the temperature. Next is de-Broglie wavelength of an electron. I want to find out what is the de-Broglie wavelength for an electron. So this is the kinetic energies formula. Okay, so we can write it down. Half mv square equal to E into V, and velocity of the particle can be found out. Now we know wavelength equal to h by mv. So putting the value of V, we get this. Now putting the value of h, m and e, these are constants, we get that the wavelength is actually 12.27 by root V. 12.27 by the root V. V is the potential between the plates. Next, let us see the numericals now. Okay, we have to watch the numericals now. Okay, so please watch the numericals now. So first numerical, they are saying that the threshold frequency for a certain metal, this is nu zero, is this: if the light of frequency, this frequency is incidented on the metal, predict the cutoff voltage. So we know this is the formula, this is our formula. V naught is the cutoff voltage, value of the E, that is charge of electron, I know, H I know, okay, incident light frequency I know, minimum H nu zero, this I know, phi equal to H nu zero, and nu zero also we know. So putting all the values, we can find out the threshold frequency, which is 2.03 V. V is the stopping potential. This is the volt. V naught is the stopping potential, and this is the volt. Work function of sodium is given, so phi 0 is given to us, phi 0 work function. Does the sodium show photoelectric emission for orange light? So let's find out first what is the minimum frequency, minimum wavelength required. Phi naught equal to h nu 0, which is c by lambda 0. From here we can find out the work function of it when orange light is incidented. So what is the work function of this? Using this is the wavelength of the orange light which is given. So this is the wavelength of the orange light. Okay, so using the formula C, this is h c by lambda and if I divide it by 1.6 into 10 to the power minus 19, I will get it into electron volts. That means the minimum work function required to eject electrons is 1.8 electron volt, but here the work function is given 2.3 electron volt. That means this is very less than this, so emission is not possible. No electrons will be emitted. Next, as you can see, the work function phi naught is given to us. Find the threshold frequency for cesium. H given. Okay, so this is given to us, H is given to us, nu 0, we can find the threshold frequency, we can find. Now they are telling the wavelength of the incident light if the photoelectric current is brought to 0 by a stopping. So this is the V0. So using this formula, the wavelength of the incident light can be found out. Putting all the formulas, we get the values, which is 554 nanometer. 554 nanometer. Okay friends, let's see the next sum. The next sum says that wavelength of the light falling, the wavelength falling is this on the sensitive plate. This is the incident wavelength. Work function is this. Energy of the photon in electron volt. Okay, energy is h nu. Energy is h nu, which is hc by lambda. So lambda incident I know. So we are dividing by 1.6 10 to the power minus 19 to convert the joules into electron volt. How to do that? Divided by 1.6 into 10 to the power 19. So here we are dividing and the answer is coming this. So this is the energy of the incident photoelectrons. Next is kinetic energy. Work function given. Kinetic energy of the photoelectrons. First of all, this is our formula. Phi naught is given to us 1.90 and this incident is given to us 4.28. We found out, which is this is the kinetic energy of the photoelectrons. Next, stopping potential. So phi naught from here, stopping potential. Okay, we know that phi naught is equal to, we can use it like this, phi naught is equal to EV0. Okay, so this is the stopping potential. So we can easily calculate it. They are telling find the kinetic energy of the photoelectrons emitted, the stopping potential. Okay, so we know h nu, we know E, this is the incident, this is the work function. So kinetic energy is equal to h nu minus work function, and this is E into V0 is equal to h nu minus phi 0. So this whole I know, divided by E, I will get the V0. This is the answer of this. Next, a sheet of silver is illuminated by a wavelength. So this is the incident wavelength. What is the maximum kinetic energy of the emitted photoelectrons? Threshold wavelength is given to us this. Okay, so we know this formula. Nu equal to C by lambda. C I know, H I know. So this is the incident wavelength and this is the minimum wavelength required. So putting the values, we got the kinetic energy. That is what they were asking, what is the maximum kinetic energy of the photoelectrons. Next, the work function of cesium is this. This is phi naught. Work function I know. Light of this much wavelength is incident on it. Find the threshold frequency and threshold wavelength. Okay. First we know this formula. So we have to find out nu naught, threshold frequency. So this is given 1.8 electron volt. So into 1.6 10 to the power minus 19 will give you in joules. And this is the value of H. So we have to find the value of nu naught, that is threshold frequency we got. And now we need maximum kinetic energy of the photoelectron. So this is the maximum kinetic energy, h nu minus phi naught. So h nu is hc by lambda, h into c by lambda, minus phi naught we already calculated, 1.8 electron volt into 1.6 10 to the power minus 19. This is the joules. So we can calculate the maximum kinetic energy of the photoelectrons emitted. Okay, then we will find out what is the maximum velocity of photoelectrons emitted. So let's see. So we know kinetic energy is half m V max square. So V max we have to find 2 ke by m. Putting the value of ke and m, we calculate the velocity of the photoelectrons. Next, they are asking if the intensity of the light is doubled, what will be the maximum kinetic energy? Intensity doubled. Intensity, if you double it, then the effect on the kinetic energy. So see here, kinetic energy of emitted electrons is independent of the intensity of the incident light. Very important word. That means whatever is the intensity, it's not the factor. Kinetic energy of the emitted photoelectrons is independent of the intensity of the incident light. Clear? Next, as we can see, kinetic energy equal to half m V max square V max. So we can find out this, sorry. The work function of aluminium is this. This is phi naught. How much potential difference will be required to stop emission of maximum energy electrons by a light of 2000 angstrom? So as you can see here, that the work function of the aluminium is given to us, and so this is the work function of the aluminium phi naught, and they are telling how much potential difference will be required. So V they are asking to stop emission of the maximum energy electrons with the light of this. Okay, so we know that work function is given to us, and wavelength, their incident wavelength is given to us. So we know this is the equation of the photoelectric, Einstein's photoelectric equation is this, E equal to E into V0. Okay, this is the potential we need to stop. So V naught. So V naught is what we have to find, because we have to stop the electrons from getting ejected. So E, so this is the E into V naught equal to HC, H into this is the AH, C, this is the lambda, and this is the phi naught. This is 4.2 electron volts. So 1 electron volt is 1.6 10 to the power minus 19 joules. So solving it, we get this on the right side. So V will be this by 1.6, and which is coming 1.98 volts. This is the volt we have to use to stop the electrons being emitted. What will be the wavelength of that incident light for which stopping potential will be 0? Okay, so now see, they are telling that, so we know first of all this is given to us V naught. So they are telling stopping potential should be 0. So if it is 0, then this is the equation coming, and we have to find the wavelength. So this is the wavelength formula. So putting the values, I know H, C, and work function for the metal remains the same. So calculating, we get the wavelength of the light. Okay. Next, the graph shown. See, they have given us a graph in which this is the kinetic energy of the ejected electrons. As you can see that this is the kinetic energy ejected, and this is the frequency. So this is the threshold frequency, this value. Okay, so first question is find the threshold frequency, and it is coming between 2 and 4. So I think it is, the threshold frequency is 3 into 10 to the power 14, because it is, this value is 3, this value is 3, and here we have to do into 10 to the power 14. So this is the threshold frequency. Next, they are telling work function of the metal. So first of all, see here, this intercept on the x-axis intercept on the x-axis shows it is minus 2 into 10 to the power minus 19. Okay, and that is the work. This is a negative. That means this much of kinetic energy is the negative, which is not allowed to come to the plate A. Okay, so work function will be the intercept on the y-axis, which is this much of joules, and if I divide by 1.6 10 to the power minus 19, this is the work function. Now they are telling Planck's constant. So work function is also written as hc by lambda. Hc by lambda is the work function because intercept on the axis is given as hc by lambda, which is h nu. So we know the work function given to us. We know the work function. Okay, 2 minus 2 into 10 to the power minus 19 h, and frequency, threshold frequency, we know that. Using that we can find out the value of the h. Next they are asking maximum kinetic energy of the ejected electrons by a light of frequency this. So incidented frequency is given to us, h I know, work function remains constant, so putting the values we can calculate the value of the maximum kinetic energy. Clear? Next, when a piece of metal is illuminated by a monochromatic light of wavelength lambda, stopping potential for the photoelectric current is this. So this is the stopping potential when the wavelength is lambda, and when it is illuminated by this wavelength, then stopping potential becomes V naught. Okay, so first of all let us write the equations. So as we know, this is our equation for photoelectric effect. So first of all, when the stopping potential is lambda, stopping potential is 2.5 V naught, the wavelength is lambda, and when the stopping potential is V naught, the wavelength is 1.5 lambda. So now we are doing 1 divided by 2. Okay, so what will cut out? E will cut out, V naught will cut out, so what remains? 2.5. Okay, this is the numerator, this is the denominator. So we calculate it, we multiply it, this whole thing into 2.5, hc by lambda minus phi naught, this. So what we got? hc by lambda. So we got hc equal to this value. Okay, now they are telling find the threshold wavelength for the photoelectric emission. Threshold wavelength. Okay, so see they are asking what is the lambda naught. Okay, so we know work function is given by hc by lambda naught, and we are asking to find this. So here hc by lambda naught, hc's value we are putting as this by lambda naught, so this cuts, so lambda naught comes out to be 2.25 lambda. 2.25 lambda. Next sum. Let's see the next sum. Find the frequency of so friends, they're telling find the frequency associated with the photon of energy, this joules. Okay, so this is the energy given. Okay, this is the energy given, find the frequency. Okay, so hc by lambda is equal to this. This is the energy is h nu, which is hc by lambda. This is h nu given to us. They are asking to find the nu, so this by h we get the frequency. Next, find the energy and momentum. So energy is hc by lambda, we put the value hc lambda, wavelength is given to us, this is the energy. Now they are telling momentum equal to h by lambda, momentum is h by lambda, so this is h, this is lambda, we get the momentum, kg meter per second. Next, they are asking find the frequency of the light given. Frequency given to us. Power is this. Power is this much watt, which is joules per second. Joules per second. Now, what is the energy of the photon? So energy is h nu. So h into nu, which gives the energy. Second, they are asking how many photons per second are emitted by the source. So number of photons per second will be, it will be the power divided by the energy. Power divided by the energy. So these many photons per second will be coming out. Next, find the wavelength lambda of a photon and de Broglie wavelength. The wavelength is lambda of the de Broglie wavelength of an electron have the same values. That means de Broglie wavelength of a photon and the de Broglie wavelength of an electron are same. Show that energy of the photon is given as this. Okay, this times the kinetic energy. So see, kinetic energy of an electron is half mv square, which is half m square v square by m. So this becomes the momentum. Okay, and momentum is h by lambda. So we get the kinetic energy of the electron is this. Now energy of the photon is hc by lambda. So they are telling energy of the photon by energy of the electron. Let us compare and we get this. So this is the answer. Next, an electron of alpha particle and a proton have the same kinetic energy. So alpha particles, electron and a proton have same kinetic energy. Which one of the particles has the shortest de Broglie wavelength? So see, we know energy of the electron, energy of the alpha particle and energy of the proton will all be same. So this is the energy of the electron, proton, the alpha particle and proton. Okay, an electron of an alpha particle and a proton have the same kinetic energy. So we can write this. Now, so we know that the mass of the alpha particle is 4 times the mass of a proton. So we wrote that. And this is the mass of the proton. Okay. So now, cutting out, and the mass of the electron is, we know that the mass of an electron, if it is 1, proton is this, and this is the proton. So cancelling out, we get VE square equal to this much, V alpha square equal to this much, VP square. So now watch one thing. We know V equal to nu lambda. We know that. Okay. So this becomes nu square lambda E square, nu square lambda alpha square, nu square lambda P square. So nu square cuts out. Okay. So we get from here, what do we get from here? We get lambda square, we get lambda E square equal to 4 into 1836 lambda alpha square equal to 1836 lambda P square. So definitely we can see that the shortest wavelength will be for the alpha particle, right? Next, a alpha particle is moving 3 times as fast as an electron. Okay, so velocity of the alpha particle is actually 3 times the velocity of the electron. The ratio of the de Broglie wavelength of the particle to that of the electron is this. So the wavelength ratio is also given. So see, this is the wavelength ratio of the alpha particle to the electron given. Calculate the particle's mass and identify the particle. Okay, so see, this is the kinetic energy of the proton, kinetic energy of the proton and kinetic energy of the electron. equal to HVP by lambda P, HVE by lambda E, because kinetic energy is half mv square, and also it is equal to hc by lambda. Okay, and here c will be taken as v. So using this, half of cuts, this velocity of the proton is 3 times that of the alpha electron, so that is why 3ve square. So ve square will cut. So what remains is this. Okay, now mass of the electron is 9.11 into 10 to the power minus 31 kg. So 3, that means we can write it like this, as we have to find out the mass of the proton particle. So this is 3 lambda E by lambda P, and now they are telling that the lambda E and lambda P ratio of the de Broglie wavelength to that of the particle. Okay, lambda P by lambda E is given to us, so putting this value here. So only unknown is MP, mass of the proton, which is coming to be this. Now the value of this shows that it is actually a neutron or a proton, because this is the mass of a neutron or a proton. Next, what is the de Broglie wavelength associated with an electron accelerated through this? So we know that this is the formula. This is a direct formula where this is the wavelength of de Broglie and this is the potential difference. So putting the potential difference, we can calculate this, or we know that E into V equal to Hc by lambda. Okay, so we have to find out the wavelength. Value of E I know, potential I know, H I know, C I know, and wavelength I can find out as this. Find the de Broglie wavelength of a neutron at this temperature, and mass of the neutron given. This is the Boltzmann constant. We know that at this temperature, so what is the Kelvin temperature? It is 400 Kelvin, and we know energy is 3 by 2 kT. Energy is 3 by 2 kT. So 3 by 2, value of K into T. So this is the energy. And also we know P equal to H by lambda. P equal to H by lambda. Lambda equal to H by P. So what is P? P is equal to 2 into M into E. E is the energy. Okay. M is the mass of the proton. H is the Planck's constant. All values are given to us. Energy we found from here. This is the energy. So putting it, we get the wavelength of the de Broglie wave. What will be the de Broglie wavelength of an electron having this much energy? So again, same thing. Lambda equal to H by 2 mk. The value of the kinetic energy is given to us, 500 electron volt, means this is the joules. Mass of the proton given, H I know, so we can calculate the wavelength. The wavelength of a photon, so this is the lambda given, collides with an electron. Its wavelength after collision is this. Okay, so we have to find the energy scattered. So this is the, so we know that energy, incident energy is equal to Hc by lambda. So energy will be incident energy minus energy after collision. So incident energy is Hc by lambda incident minus Hc by lambda after collision. So here we are using lambda 1 is after, before collision, after collision. So we are using the values and we are calculating that this is the energy which is getting dissipated by the electron. Next, the stopping potential is given 0.82 volts, and it is required to stop the emission of photoelectrons from the surface of a metal by a wavelength this. Okay, so see, this is the formula. So stopping potential is given to us already, wavelength is given to us. Okay, so they are telling this is the stopping potential if the wavelength is this, and this is the stopping potential if the wavelength is given as this. So let us write down for the first wavelength. This is the equation. Okay, stopping potential is given as 0.82 E hc by wavelength given phi naught. For the second it is given 1.85 and wavelength is given. So if I divide these two, okay, so from the first we separated the work function, and now we are putting it in the second equation. We are putting the value of the work function here. So on calculating this, we are getting these values, and now putting the values of, they are telling find the value of H. Okay, so from here H we can calculate, and this is the actual value of the H. Next, light of wavelength. This is the wavelength given. The photoelectrons emitted describe a circle. Okay, so this is the photoelectrons describing a circle. Radius given to us. Magnetic field B given to us. What is the work function in electron volt? First of all, we know that mv square by r is equal to bqv. This is the velocity of electron, this is the velocity of electron, this is the magnetic field, this is the charge, this is the radius. So from here 1 v cuts, and we are getting v as this value. Now question is, from here first of all I have to find out the value of the, they are asking what is the work function in electron volt. Okay, so first of all we calculated the value of the velocity. Now we know this is the equation. The kinetic energy emitted is equal to this. So from here the velocity I know. This phi naught, I will separate the phi naught. So phi naught separated. Now put all the values h, c, lambda, 1 by, this is the m, and this is the v square. So putting and calculating, we get this is the work function of the photoelectrons. Now there is a 200 watt lamp, power given, power is this, which is 200 watt lamp emits a yellow light of wavelength this much micrometer. So this is a wavelength. So this is the lambda. Assuming it to be 25% converting electrical energy. That means out of this power only 25% energy will be converted, which is giving 50 joules per second. This is the energy, and we know energy equal to hc by lambda. Clear? So hc lambda, so this is the total energy emitted, and per second it can emit 50 joules. So how many photons? So it will be power by the energy, power by the energy. So 50 by the energy. So this is the number of photons per second. Next, find the strength of the transverse magnetic field. So B I have to find, required to bend all photoelectrons within the radius r I know. So same way, and lambda is given to us, work function is given to us. So first of all bqv equal to mv square by r, 1 v cuts. From here we find out the v first of all. Now we know for photoelectric effect this is the formula, where E equal to half mv square. Now putting the value of v, so this is the value of v here. v square. Okay, so now what we are doing, 1 m cuts, this is the value. So we have to find out the work function. That means we have to separate the phi naught from here. Okay, sorry, we have to find out the magnetic field B. So we have to find out the B, correct? So this is the Q, this is the R, this is the M, equal to HC lambda minus phi naught. So calculating this, we found out the B square is coming this. So B will come, the B square will be 2 into this, so B will be root over this, which is the value of this. So this is the value of the magnetic field required by the transverse, by the photoelectrons to make a circle of 50 centimeter. So friends, with this I have completed the discussion of the magnetic field, of the dual nature of the light. We have completed the discussion of the dual nature of light, and I hope you have understood it. We have discussed the dual nature of light, and we have also discussed a lot of numericals, concept, theorems. Okay, so I have tried to cover up the maximum variety of the numericals based with this chapter. It's a very, very important chapter of class 12. So hope you have understood it, and if you have really any problems, you can please contact me over this number. I will give you all the suggestions and the doubt clearing things in this. Okay, so please keep watching Parijat sir classes once more, and like, share and subscribe. Definitely do it for the motivation to make more and more videos, and so that you can share it to many others who cannot follow the book, or to whom the book is becoming more and more tough. So here I am discussing all type of concepts, including the numericals. So hope you have understood. Okay, so thank you very much. Till then, it's goodbye from my side.